Welcome to lesson 8.1, Find Angle Measures in Polygons. So before we get into this lesson, what you want to keep in mind is chapter 8, which obviously we're beginning now, is all about quadrilaterals, meaning four-sided polygons. And then we're going to expand into a few other types of polygons as well. But the main idea is going to be back to the idea of quadrilaterals and polygons. So first thing is, remember, a polygon is made up of line segments that connect at their vertices or endpoints, and it creates a closed figure, meaning they all connect at their endpoints, no open space. So in a polygon, two vertices that are the endpoint of a same line or same side are called consecutive vertices. So for example, B and C are consecutive, as well as A and B and C and D. Because BC are the endpoints of side BC, AB, A and B are the vertices of that side, CD, C and D are those vertices. A diagonal of any polygon is a segment that joins two non-consecutive vertices. So in our polygon over here, A, B, C, D, E, our diagonals could be segment BE if we draw that in, or segment BD. So they are segments that connect non-consecutive vertices. So if we were using B as our starting point, BE and BD. Another option could be if we use C, CA and CE. So examples of diagonals. Now, moving on from definitions into theorems. So our first theorem that we're looking at is 8.1, the polygon interior angles theorem. So what this theorem states is the sum of the measures of the interior angles of a convex n-gon, meaning number of sides for n. So a convex n-gon is, in parentheses, n minus 2 multiplied by 180. So simply put, if we want to figure out all the angle measures, what they add up to on the interior of any figure, it's your number of sides minus 2 multiplied by 180. So in this case, if we had 6 sides, it'd be 6 minus 2, which is 4, and then multiply it by 180. Now, the corollary to theorem 8.1 is the interior angles of a quadrilateral. So a corollary is something that can easily be supported or proven by a theorem. So what this corollary states is that the sum of the measures of interior angles of a quadrilateral is always 360 degrees. So any four-sided shape, the interior angles always add up to 360 degrees. And we could check that with our expression here. 4 minus 2 multiplied by 180 equals 360 degrees. So example 1 is looking at this idea of the theorem and asking us to find the sum of the measures of the interior angles of a convex octagon. So we know octagons have 8 sides. So if we're putting it into the expression, n minus 2 multiplied by 180, 8 minus 2 is 6. 6 multiplied by 180 is 1080 degrees. In example 2, it says the sum of the measures of the interior angles of a convex polygon is 900 degrees. So they're giving us the total angle measure. Now they want us to be able to use that info classify the polygon by its number of sides. So we're still using this expression, n minus 2 in parentheses multiplied by 180 equals, and in this case we knew our angle measure total of 900. So to solve for the number of sides, we divide by 180. So n minus 2 would equal 5. Add the 2 to each side, and n would equal 7. So we know that's a 7-sided polygon, which we could also call a heptagon. Then we get down to examples 3, parts A and B. First off, we'll look at the coin in part A. It says the coin shown is a regular 11gon. Find the sum of the measures of the interior angles. So if we know it has 11 sides, 11 minus 2 multiplied by 180. So 9 times 180 gives us 1,620 degrees. Then in part B, it says the sum of the angle measures, or interior angle measures, of a convex polygon is 1,440 degrees. Classify the polygon by the number of sides. So again, they gave us the total, 1440, so that would equal n minus 2 in parentheses multiplied by 180. So again, to find the number of sides, we divide by 180, n minus 2 equals 8, add 2 to each side, and n equals 10. So we know that polygon is 10-sided, meaning it's a decagon. You could also call it a 10gon, just like here, an 11-sided figure is called an 11gon. Then we get down to example 4. This is now where we need to do a little bit of algebra to find the value of x. So what we have here is a trapezoid, so a 4-sided figure. So I know the total interior angles add up to 360 degrees of any quadrilateral. So to figure out the value of x, I need to add up the 3 interior angles that they gave me and take that away from 360. So it'd be 360 minus those 3 angles added together. So 360 minus 288 would give me 72 degrees for the value of x. Now in 5, we have parts A and B. First, we'll look at A. Use the diagram at the right to find the measure of angle S and the measure of angle T. Well, they put an arc on T and S, meaning they are congruent. So S and T measure the same amount. I know in this case I have a pentagon, 5-sided figure. So my total angle measure, 5 minus 2 times 180, is 540 degrees. So I know all the angles in this pentagon have to add up to 540. So if I would do 540 minus the 3 angles I already know, so 540 minus 334, that gives us 206 degrees. But to answer for angle T and S, that's 2 angles left. So I need to take the 206, divide it by 2, and angle S is 103 degrees. Angle T is 103 degrees. And then in part B, it says the measures of the 3 interior angles of a quadrilateral are 89, 110, and 46 degrees. Find the measure of the 4th interior angle. So again, it's a quadrilateral, so we know the total is 360 degrees. Subtract the 3 angles we already know added together, and we're left with 115 degrees for our missing angle. And then we'll look at the idea of exterior angles. So we also have a theorem to go with that, but first let's just look at the paragraph above. It says exterior angles. Unlike the sum of interior angle measures of a convex polygon, the sum of the exterior angle measures does not depend on the number of sides of the polygon. The diagram below, which we'll look at, suggests the sum of the measures of the exterior angles, one at each vertex, of a pentagon is 360 degrees. So in general, the sum is 360 degrees for any convex polygon. So not interior angles, but exterior angles, the sum of the exterior angles for any convex polygon, whether it has 3 sides, 12 sides, 300 sides, those would add up to 360 degrees. And so that gives us theorem 8.2, polygon exterior angle theorem, which says, just like I said, the sum of the measure of exterior angles of a convex polygon with one angle drawn at each vertex is 360 degrees. So if we look at this being our pentagon on the interior, our exterior angles, one at each vertex, would be angle 1, 2, 3, 4, and 5 here. Those angles around the exterior will always add to be 360. So our last two examples. Example 7, what is the value of x in the diagram shown? So I know that all my exterior angles, these four angles, have to add up to 360. So x plus 2x plus 89 plus 67 equals 360. So that'd be 3x plus 156 equals 360. Subtract the 156. 3x equals 204. Divide by 3. And x equals 68 degrees. And then in our last example, it says a convex hexagon has exterior angles with the measure of 34, 49, 58, and 67, and 75 degrees. What's the measure of the sixth exterior angle? So in this case, we would add up the 5 that they gave us and take that away from 360 degrees. So 360 minus those 5 added up, which is 283, gives us 77 degrees for our missing exterior angle. So the key to this lesson is exterior angles of any convex polygon always have a sum or add up to 360. And for interior angles, it's the number of sides minus 2 and then multiplied by 180 degrees.